Hi, hello, and good day to everyone. My name is Arvindan, son of Tyagarajan, and my metric number is MA19143. Today, I'm going to present about our project, our CFD project regarding CFD analysis of tube flow and the heat transfer in the fin and the tube heat exchanger. We are from the big group one. Under group one, we have five members. One is me, myself, Arvindan. Next is Kavin Kumar. Then Mahadevan. Then Shamirul Fami. Last person is Mohammad Alazik. Next, today I'm gonna present about the background of a project. So, compact feed and tube heat exchanger are frequently used in the wide variety of power and petrochemical engineering applications, including the automotive radiations, HVAC, evaporator, condenser, food processing, and other fields also. The sum of the air side convection thermal resistant, liquid side convection thermal resistant, and wall convection thermal resistant determines that overall thermal resistance for these types of heat exchangers. The heat transfer coefficients on the air side is notably low as the result of the air poor thermophysical characteristic. As a result, the head side exhibits the greater thermal resistance. The example of the common material they are used are aluminum and steels are the nearly all of the tiny pin tube and heat exchangers in the market. These are the pricey and nervous and corrosive. Next is the consequence of the using this kind of the flow for the experimental is time consuming for expensive and then difficult to carry out the experiments for the carry out the data. Furthermore, it is nearly impossible to visualize the flow and heat transfer inside the exchanger. Therefore, a numerical solution research may be the best choice to visualize the flow and heat transfer process inside an heat exchanger while along also lowering the expense associated with the experimental studies. The simulations are simpler to run, produce findings are more quickly, and they make it simple to monitor the flow and heat exchange transfer phenomena inside the heat exchanger. Objective of our project is there are three main objectives: to visualize the velocity and temperature changes inside the compact feed and tube heat exchanger. Next is to investigate the heat transfer coefficient and the pressure drop at the various conditions. The last objective is to develop steady and incompressible flow model for the compact feed and tube heat exchanger using the CFD simulation program called Fluent. Next is the project scope. In project scope, this project involved using the Fluent simulation software to model the steady incompressible flow in compact feed and tube exchanger. The project scope was about the create the numerical model of using the Fluent to simulate the flow and heat transfer with the heat exchanger. Then it also to visualize the velocity and the temperature distribution between the heat exchanger body along with the investigation of the effects have flow rate, tube arrangement and material types, tube diameter with the heat transfer coefficient and pressure drop. Lastly, the main scope of to provide detailed result and conclusion on the finding of the CFD simulation. Thank you. My friend will be continue.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Al-Haziq. So I will present the problem description. So in this project, a steady state incompressible fluid flow through a two-dimensional airflow through a small fin and tube heat exchanger as depicted in figure 1 will be the problem to analyze. So in figure 2 depicts the computing domains for the numerical analysis for both the staggered and inline test section. So A is inline and B is staggered configuration. So the portions shown by the dotted lines in figure 2 can be chosen as a computational domain because of the symmetry of the geometries. To further verify that there is no flow disruption and the velocity profile is uniform when it reaches the fin and tube surface, the computational domain is additionally expanded by 1 time the tube transverse pitch, which is 30 mm. Air at room temperature is used as the working fluid, and figures for its density, viscosity, thermal conductivity and specific heat capacity can be found in books or other relevant sources, while the fins are made of a variety of material and should be listed in table 1 as we can see in the slide, the table 1. So this is the properties of material, which is aluminium and CNT resins composite. So for the procedure, we make sure all the meshes chosen for the analysis meet the mesh quality metric first to ensure that the simulation results are not changing with different mesh values. Execute a mesh independent test using at least 5 distinct mesh size. Additionally, make sure that the meshes near the walls are smaller than those farther from the walls. And then after choosing the proper grid size, simulate the boundary condition list in table 2 as you can see, and validate the model by contrasting the simulation result for the average temperature distribution with the equivalent experimental data list in table 3. So aim for an inaccuracy between the simulation and experiment result of no more than 10%. So third, continue the simulation for the various operational parameters indicated in table 2 once the model has been successfully validated. So this is the mathematical formulation. So first we have continuity equation, momentum equation, we have x momentum equation and y momentum equation. Some other equation was used in order to find the heat coefficient, the pressure drop and the mean temperature along the heat exchanger. So that's all from me. Thank you.
Hello everyone, my name is Madhavan son of Sivaraman, metric ID MA19090. Today I would like to talk about the metrology part of our project. Now let us look on the pre-processing process. For the case, same diameter with initial velocity 1.8 meter per second. For the fluid flow, fluid analysis, model geometry, a 2D compact fin and tube heat exchanger has been drawn by the considering all the dimensions as follows. Length and width of the fin 330 by 30 mm, diameter of the tube 3.175 mm, length of the tube 19.5 mm, and then distance between each tube is d30 mm. And then for the second step, we need to identify and plot the mesh boundaries for this geometry using the name selection for edges and surface. So basically here we have the inlet, outlet, surface body and wall tube exchanger wall. For the third step, we can clearly see that after the mesh boundaries, we need to input the inflation command for the geometry on a single face utilizing face selection option, which is for the boundary of 28 edges totally using box selection mode. So basically for the inflation option, we select first layer thickness, which gives the height of 0.0016 mm. We need to alter it, and then the maximum layer is 10, and then we have the constant rate of growth, which is 1.2. For the fourth step, the edging size are represented as follows. For the scoping method is name selection, and then of course the name selection is based on the surface body. We need to see the meshing, and then the element size is 0.025 mm. Now let us look on why we choose the 0.025 mm mesh size as I mentioned here before. So basically we done the mesh test for the 0.2, 0.25 and then 0.025. Under the skewness and orthogonal quality, we can clearly see that the orthogonal quality and skewness for the 0.025 is actually better compared to 0.25 and 0.2, which gives us the very good quality. Thus we check this mesh, and it's actually appropriate for us to use this mesh quality for a better analysis. Now let us look on the processing, which is solver. First we need to set up the process as startup for the criteria such as double precision and also the solver processing input, which is 2. And then we need to check on the general manager option, which is type is actually based on pressure based, velocity formulation is under absolute, time is steady, and also the 2D space is under planar. Now let us look on the viscous module setup. For this analysis, we need to set up for the K epsilon, which is 2 equation, and then for the near wall treatment, we need to set up for the enhanced wall treatment. For the material, air is selected with a density of 1.185 and also the viscosity is 1.831 with a power of -0.5. Now let us look on the solid. So for the solid material, as we can see, we choose for the aluminium, which is actually altered for the CNT. So our project is basically related on the CNT resin composite as instructed by the project details. So we use the CNT resin composite, which gives us the density of 1.75. So we will input the 1.75 value inside the density there. And then for the energy equation, we need to check in the energy equation to enable the thermal value input option. The next step is we need to set up the boundary condition, which is inlet. The velocity magnitude was given as I mentioned earlier is 1.8. So we input there, and then for the thermal value is set for 300K, which is actually the 27 Celsius is actually converted to 300 Kelvin. Now let us look on the outlet. For the outlet, we can see that the specification method is intensity and hydraulic diameter as same as before, which is for the inlet also. And then for the thermal value is slightly different because we follow the 100 Celsius, which is converted to 373 Kelvin. Now let us look on the wall motion. Wall motion for this case is actually stationary wall, and then at this scenario we follow the outlet temperature as well, which is 373 Kelvin. Now let us look on the reference values. Reference values is actually based on the area of the geometry size, which is 0.0099 meter power of 2. The density follow as the air. Temperature is 300 Kelvin based on the inlet because we compute from the inlet, and then viscosity is 1.831 power of E negative 0.5. The velocity is, as I say, 1.8 meter per second. For the solution method, we use the scheme of simple, and then for the gradient we use the Green-Gauss cell base. For the pressure, momentum, turbulent kinetic energy, turbulent dissipation rate, and also energy, we actually look on the second order upwind. Only the pressure is actually altered for the second order. The rest is all based on second order upwind. Now let us look on the residuals monitor, which is all the values that we plotted before this is actually altered here for the residuals monitor to give the value for the graphs and then plotting. So basically we will use for the value of 1 power of E negative 0.5 for the x velocity, y velocity, continuity, x epsilon, and also the energy. And then for the iteration we maintain, which is 10,000 units. For solution initialization, at here we use the hybrid since the energy equation is activated. And then for the run calculation, we set up the number of iteration same as solution initialization, which is 10,000 iteration, and then we will start the calculation. Now let us look on how to find the velocity contour, temperature contour, and then finally velocity vector. For the velocity contour, we need to insert the contour, and then we need to select surface body for domains, symmetry 1 for the locations, and then the variable, of course, the velocity, because we are finding for the velocity, and then we can apply and display the contours, which we will be looking on the results part. And then for the temperature contour, same as the velocity contour procedure, but we will input the variable for temperature. For the velocity vector, a bit different, which is we adding the symbol, which is arrow 3D, the sizing of 1.0 sizing, which actually gives us the clear observation of the arrows flow from the inlet to outlet along the geometry that has been drawn, which is tube and fin heat exchanger. Now let us look on the pressure drop plots and also heat transfer coefficient plots on how we actually getting the graph for these two aspects. First of all, we need to draw a line or ray created for the surface bit x0, which is negative 1 to x1 equals to 1 meter. For the solution of xy plots, the pressure and its coefficient are selected. So basically we focus on the pressure drop plots. So the variable need to select from the pressure and also its coefficient for the y-axis, because y-axis gives us the outcome under the y-axis. So the existing line that has been selected is need to be displayed, because the line is actually help us to identify the pressure drop plots at each tube and also along the geometry from inlet to outlet. For the heat transfer coefficient plots is actually same as pressure drop plots, but we select the wall flux replacing the pressure and also surface heat transfer coefficient replacing the pressure coefficient. And also for heat transfer coefficient plots, we need to select a new plots by not altering the pressure drop plots, which is actually give us the value outcome for the heat transfer coefficient plots. So that's all from me. Thank you.
My name is Kavin Kumar and my ID number is MA19020. So today I'd like to give an explanation on the result that we have made, the CFD analysis of the flow and the heat transfer in the fin and the tube heat exchanger as well. So during the result segment, the velocity vector, the velocity control, and the temperature control will be explained one by one. As we can see, the residual history is the first main part that needed to be done to monitor the behavior of the numerical process. Importantly, they have indicated and showed us whether the solution show a trend of convergence and divergence. In case there is any divergence have been made, we have to rerun back the iteration with a different number of iteration and different mesh as well. As the next first one is the flow and the temperature visualization result between the inline tube arrangement and the staggered tube arrangement. As for the left side shows the staggered tube arrangement, which is the heat flow is a bit less in the outlet area. As we can see in the velocity control between the inline tube arrangement, the heat flow is very good from the inlet and the outlet. This shows that the inline tube arrangement is having a good heat flow from the inlet to the outlet than the staggered tube arrangement. As for the velocity vector have been made from the different type of twin, which is the left side shows the composite CNT composite resin, and the right side is the right side velocity vector shows the aluminum type of twin. As we can see that the heat flow is very good in the the velocity flow is very good in the CNT composite resin, as it allows a much more heat flow than the aluminium, because the CNT composite resin is having a good and a greater heat thermal conductivity than the aluminium as well. And the temperature contour has been made with the different tube diameter, which is 3.75 mm and 6 mm and 7 mm. As we can see, the temperature contour, it is there is changes have been made from the diameter, which is this is a bit smaller. The next one is a bit bigger than the right side, and this one is the biggest. As you can see, the heat flow is reduced in the area of the tube diameter as the diameter is been increasing. And after the made of contour, the effect of some parameter on heat transfer coefficient and pressure drop have been made across the inline arrangement heat exchanger, which is the first one is the heat transfer coefficient. Whenever we see the graph of the heat transmission, you can know that the heat transfer flow is being reduced as the heat is flow from the inlet to the outlet area. And same goes to the pressure drop as well. Whenever flowing towards from the inlet to the outlet, the pressure drop been increasing as well. And the next one is the parameter across the different size of tube diameter. As I've said informed earlier, the diameter of the tube that be taken is 3.75, 6.5 and 7.5 as well. As we can see that the pressure drop is being increased significantly when the tube size diameter is being increased. So when the pressure is highly dropped, the heat flow will be greater, so the process will be much more easier. As we can see that the right hand side shows that the heat coefficient as well, heat transfer coefficient as well, which shows that the heat transfer coefficient is increasing whenever the tube diameter size is increasing as well. So whenever the tube size diameter is increasing, the heat flow is good enough in order to flow from the inlet to the outlet area. And after the graph is being plotted, the results all were being extracted to the Excel sheet in order to came up with a bar graph. So the left side shows the pressure drop and the various tube arrangement in the inline heat exchanger, and the trend of the graph is the pressure drop is directly proportional whenever the length is increasing, which is from the inlet area to the outlet area. And the heat coefficient across the three tube location in inline arrangement shows that the heat flow is reducing, because whenever the flow is going from the inlet to outlet, there will be some more obstacles that the particles needed to be flow, so the flow will be reduced as well. And the next one is the pressure drop across the different tube diameter and the heat transfer coefficient across the different tube diameter. You can see that the pressure drop across the different tube diameter has been made from the 3.75, 6.5 and 7.5, and the pressure drop is being reduced significantly, and the heat transfer flow has been reduced significantly as well. This is because the pressure drop is increased when the tube diameter size is increased, and the heat transfer flow is increased when the tube diameter size is increased as well. So that's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Shamir Fahmi bin Shamsuddin and my metric number is MA19035. Now I will present about the conclusion part. As the conclusion, we as a group have achieved all the objectives of the project. From the analysis itself, it's got to be understood that inline tube arrangement heat exchanger has higher heat transfer coefficients and lower pressure drops than the staggered tube arrangement heat exchanger. Thus, it is most recommendable for the industry to utilize their power plant work with inline tube arrangement heat exchanger. Apart from that, we also managed to discuss the analysis process among the group, and all the knowledge gained from the lab session we implemented during the project completion. Several research were done in order to extract the detail from the SC software to Excel sheet in order to plot the graph, which was crucial for the last part of the project. That's all for our group. Thank you.